Today, we are wrapping up our AC circuits, and then we are going to start on completing Maxwell's equations. The thing we still want to do is the AC circuit that includes both inductors and capacitors. There are these resonances that will appear, and analyzing those resonances will help us determine whether we can build interesting circuits with those components. And the answer is obviously yes. So we'll talk about that so-called Lrc resonator. And then I also want to spend a little bit of time talking about non-ideal circuit elements, because as you might imagine, if you take a conducting wire and you wrap it into a loop, a coil, a solenoid, to make an inductor, you design it in such a way that you get a certain inductance. But the problem is that microscopically and from a material point of view, that wire is made of metal, presumably. Let's say that you're not using superconducting materials, which means that the wire will have a resistance. So if you want to describe the response of a real inductor, you need to also include the fact that it has a resistance. And the wire, when you look at it, also has a capacitive coupling between the various loops, and you can describe that as a capacitor. And similar things we could do with talking about resistors by themselves and capacitors by themselves. And I want to show you that now you have, even for non-ideal circuit elements, you'll have the basic components to analyze it, because these are all linear approximations, and most of the time you could do these things numerically. So we'll do that, and then we'll wrap up AC circuits. AC circuits is the last chapter that is on the next midterm, which I believe is it next week, or yeah. So that's everything in midterm 2. So midterm 2 is cumulative, meaning you should also still know parts, the chapters 1 and 2, obviously. Even though I'm not going to explicitly ask you to redo stuff with Gauss's law, you should still have that under your belt. So you cannot, you can't quite forget it just yet. Plus, when we do the final, that will be comprehensive as well, and it will be all of the chapters. So therefore, make sure that you keep an eye on that. Start studying, show up for office hours. And then the material that we're starting on today is completing Maxwell's equations. Now, Maxwell's equations, we have the 4 Maxwell's equations, and I mentioned to you that we were not quite done yet. So we started with very basic electric fields. We said, there's this electric field, and if you integrate the field over an area, you get a flux, and if you do that over closed Gaussian surfaces, you get Maxwell 1, which is that Gauss's law. And then if you take line paths through those electric fields, then if you go back to the original starting point, you will not have any potential gain or loss, and therefore the field is a conservative field. And then we expanded that later, where we said, well, if while doing that you are actually threading, making a loop around a surface area that has a time-varying magnetic flux, you need to include that in your potential. That was the EMF, so that's Maxwell 2. Maxwell 3, of course, says Gauss's law for magnetism is 0 because there's no magnetic monopoles. Maxwell 4 is Ampere's law, and Ampere's law just describes how if you have a current that runs through a wire, how it can generate a magnetic field, and that's the other formulation of Bios of R. Bios of R says the same thing, except Bios of R is a direct integration, whereas Ampere's law is the Gauss's law version that helps you in cases with really high degrees of symmetry. Now, there is there are many books that have been written about the history and the development of electricity and magnetism, and I could recommend one in particular is Dergol, From Ampere to Einstein. It is really very interesting to read. So when you hear that one law is named Gauss's law and the other name is Faraday's law, you might be tempted to think that this is a one-man show, but unfortunately that we don't have enough space to give credit to all the people that contributed to this field. So so unfortunately, sometimes names get dropped. And for instance, Maxwell's equations. Maxwell didn't come up with all of these equations. He but he is remembered for one specific thing, is that he kind of gathered the whole thing together. So we already knew Gauss's law. We already knew Ampere's law. But he really kind of pulled it together. And then you notice that there was something missing in Maxwell 4, Ampere's law. So that part that's missing, we're going to describe today, and it's an important concept. It's called the displacement current. It's that thing that you need in order to see that you can generate electromagnetic waves, and they're actually already in Maxwell's equation. So we'll expand Maxwell 4, and then therefore we will add his name to the credits. So it will be Ampere Maxwell's law, and we'll do that towards the end. And again, that part we're going to the next chapter. I think that's chapter 7, and then we'll start doing electromagnetic waves. Chapter 7 is not on the midterm, the second midterm. I don't know why I still call them midterms, because they're not in the middle.
Lrc circuits. There are many Lrc circuits. The first one that we talked about already was just a combination of an inductor and a capacitor. And if you put these things in series like so, then there's this resonant frequency that occurs where you get the resistance, or rather the impedance of this circuit to go to 0 for a very specific resonant frequency. And I want to tie that to our generalized theory for AC circuits. So we had this very general description for if you have an impedance here and an impedance there. So this is Z2. And if you do this thing called impedance bridging, then you get the output phasor here and you apply the input phasor here between these two terminals. And then this transfer function is by definition, how much of output over input you get. So it's dimensionless. And it is going to be that Z2 over Z1 plus Z2, or in other words, 1 over 1 plus Z, Z1 over Z2. Z1 over Z2. So we can apply this this calculation for the transfer function to a network that contains not just 2 circuit elements, but more than 2, as long as we can make it into something that looks like this. So let's use the following. So we'll put an inductor here, and we'll put a capacitor here, and then we'll put a resistor here. Resistor, capacitor, inductor. So we still have our output here and our input here. And this is our capacitor, this is our inductor. And our transfer function, if we go using this analysis, we see that R takes the role of Z2, and Z1 takes the role of these 2 that are in series. So it should be 1 plus, okay. Now, Z1, series of these 2, so that's I omega L plus 1 over I omega C divided by R to the power minus 1. So that's our transfer function. And we can already kind of see what's going to happen to this transfer function, because let me write it a little bit differently. So we have 1 plus I times omega L minus 1 over omega C divided by R to the power minus 1. And you see that this is still that resonant condition that we had for just the inductor and the capacitor, because that is still, that's this impedance. That impedance still goes to 0 if you're at that very specific frequency where these two impedances exactly cancel. So the resonant condition is still where this part is 0, and therefore that is omega L is 1 over omega C, or omega squared is 1 over L C, or omega 1 over root L C. And that's that same resonant frequency. So we have defined that resonant frequency like this. All right. Now, that's the resonance. So what does that mean for the transfer function? Well, at resonance, this impedance goes to 0. So 1 plus 0 is 1. Take the inverse, it's 1. So at resonance, the transfer function is perfectly transmitting. So is 1 at omega naught. What happens when you're not at resonance? Well, this is where this circuit becomes different from the simple low pass and high pass filters that we discussed before. So at lower frequencies, so we go lower than this frequency, this impedance becomes smaller and this impedance becomes bigger. So the difference becomes a number that is bigger. So therefore, 1 plus something that's bigger becomes a reducing, smaller, becoming an increasingly smaller transfer function. At higher frequencies, this impedance becomes higher and this impedance becomes lower. So that means this term again becomes higher. So on both sides of this resonant condition, the transfer function decays. So schematically, we can draw this as follows. So we'll have the transfer function, and let me just draw the absolute number, absolute value. And right here at omega naught, we're at the resonance. And then below goes down and above goes down. And this resonator looks very similar to a mechanical resonator. You know, you got some kind of a damping term, you got two things that are competing and give you different orders of omega. And so at a very specific frequency, you get a peak, and then afterwards it goes down. Okay. Now we have qualitatively what this curve looks like. Now let's do this quantitatively. So the first question we can ask ourselves, okay, how wide is this peak? And that's going to be a very important metric for any kind of resonator circuit, right? If you use this as a filter, you want to know if you tune this filter to that specific frequency, how selective is it? Meaning, if you've got stuff here on the side, are you going to be able to reject that, or are you going to have that included in this transfer function? So let's find this width. Now we did this. We used this criterion before, where we say if this is 1, we usually call the cutoff where this is 1 over root 2. So we can do the same thing here. So this is the value where the transfer function the absolute value of the transfer function becomes 1 over root 2. And then we'll try to solve that equation. Okay, so that means that we need to describe the absolute value of this function. All right, now let's go. Absolute value. Okay, we're going to use that same trick that we used before, that there's a complex number in the denominator, and to get the magnitude, we can just take 1 over the magnitude of that complex number. And that means that it's 1 plus omega L minus 1 over omega C over R squared to the power minus 1/2. That's the transfer function. So that's the square. If we want to know what that width is, we need to solve when this equation is equal to 1 over root 2. So let's do that. We have our one over root 2 is 1 plus that's solving for the width. That's what we're doing. Now, this doesn't look too tricky, but ends up being rather tricky quite quickly. So let's go through this. So the first part's easy. We see that there's a 1 over root here, and there's a 1 over root here. So we invert it, we square it, and then we get 2 equals 1 plus, and it's the same term squared. So that's the condition. So subtract that. Okay, now get the 1 over to the other side. Okay, now we have 1 equals, and now omega L minus omega C over R squared. This is where we need to be careful, because when we take the square root here, we can have positive and negative solutions. So there are many ways in which to do this. I like keeping explicit positive, negative solutions in one equation, so you don't have to keep two basically the same equations. And the way I do that, I'll say there are two solutions. There's one where take the square root of this and it comes out to 1, and the other where you take the square root of this and it is -1. So in other words, plus minus 1 equals omega L minus 1 over omega C, and then that is divided by R. So two solutions. And now we need to solve this equation. Here we go. So we multiply by R. So we get plus or minus R is omega L minus 1 over omega C. So that's a C. C. It gets a little messy otherwise. Okay, and now we can't solve this really easily unless we work out a way to get rid of the 1 over omega. So let's multiply by omega C. So we get plus or minus R equals, now omega C, oops, times omega C equals, and now we get here omega squared L C minus 1. Now we have a quadratic equation. So let me rewrite it. So it is obvious, and plus or minus omega RC. And now plus 1 equals 0. That's a quadratic equation that hopefully you recognize. So if you remember, let me put it on the side here. If you have a polynomial, ax squared plus bx plus c equals 0, then there are two solutions, minus b plus or minus b squared minus 4ac over 2a. This is one of the few that I that I have memorized, and because I use it all the time. All right, so we can map this equation onto this polynomial if we just see that omega squared takes the role of x squared. So here we go. Our solution is going to be, so let me write it explicitly. A is minus LC. B is plus minus RC. And C is 1. And that's how we get our solutions. Now, therefore, we get omega equals minus b, so that's this one. Now, I usually, when I have to invert it, I flip the 2 so I can still positionally figure out where I was, and I'll clear that up. Now, I'm going to take the plus minus RC and I'm going to square that, so I'll get rid of that. Now, minus 4 times 1 times minus LC, so I get plus 4 LC. Divided by 2a, and 2a LC with the minus. So this one went there. This one came from here. So we're keeping track of the sign choices that way. Now, a couple of things. Obviously, when we square this, the plus minus freedom drops out, so this one goes away. When we divide by minus 2, we flip the sign of this expression again, but now we're going to flip this sign, and I will get a plus minus, and now the c's are going to cancel, so we'll get r over 2l, and now here we're going to get minus plus again. Make sure that I keep these separate. And then that's 1 over 2lc with the square root of r squared, c squared, plus 4lc. Now, there we go. This is the equation that tells us for which frequencies this omega, this transfer function hits 1 over root 2, and that's what's going to tell us what the width is. Now, there are now 2 and 2, so 4 solutions, and we'll use indices here to indicate which one we're talking about. So we have 4 solutions. Omega plus minus plus minus. Oops, I was going to use colors. Omega plus minus plus minus equals this thing. Okay. Now, there are 4 solutions. How can that be? Because we looked at this and we saw there's a peak, and the peak hits this root 1 over root 2 on this side and 1 on that side. So how are we getting 2? Well, we're getting 2 because actually some of these are not allowed. So let me show you. A very obvious one is omega minus minus. if omega minus minus is picked, we pick a minus here, we pick a minus there, we get a negative frequency, and a negative frequency doesn't really make much sense. So we're going to say, we'll do that here. We're going to say discard omega minus minus. Minus minus. Because it's less than 0. Okay, so that leaves us 3 solutions. And the question is there another one that is negative? Well, we have a plus plus, that's obviously okay, right? Because that's r over 2l, and this 1 over 2lc, this whole term is positive. So we're okay with omega plus plus. So we're going to keep that, because that one's bigger than 0. And now the only question is, what's the deal with the plus minus? And what's the deal with the minus plus? Plus minus, minus plus. So these are our only 4 solutions. All right. Well, if we want to know which one is positive and which one is negative, we need to look very carefully at these 2 terms in relation to one another. And this term is just r over 2l. This term is a little bit more complicated. So if we want to know which one is bigger, we have to compare this one to that one. It's a little bit tricky, but stick with me. So for instance, you can see that there's this c here and there's a c squared there. So we can bring the c into the square root, and then it becomes r squared plus 4l over c. And now the r squared you can factor out, and then you get r over 2l, and then you have a 1 plus something under the square root. And you'll see that this term is bigger than this term. So let me do that. So I'll rewrite it a little bit. We'll take omega plus minus is plus minus. Okay, we still got our r over 2l. And then our minus plus. And I said I was going to factor out our r. And I still have my 2l, but I was going to bring the c in. So that means I get 1 plus 4l over c. All right, so one more time. I pulled the r squared out here, and that means I need to put an r here. I put the r squared, pulled it out here, brought it in front. So now this term looks like r over 2l, but I still have the c here. And then I brought the 1 over c in. So now I have left here a 1 and the 4l over c r squared. I believe I did that right. All right. Now, hopefully now you see which one's bigger, because this term, and there's a silent 1 here, you see that this term is therefore bigger than that because it has the same prefactor. So in other words, this one is bigger than this one. So the one that's positive is where this term is positive and that term is negative. So that will be minus plus. And the other is negative. So really, we only need plus plus and a minus plus. So we are left now with 2 solutions. Plus plus, which is r over 2l times 1 plus square root 1 plus 4l over cr squared. Yep. And minus plus, which is now minus r over 2l, 1 minus 1 plus 4l over cr squared. So you have 2 frequencies. And now what's the difference? Well, the difference is actually quite interesting to see, because if you subtract this this term from this term is canceling, and this one stays. So it's R over L. So after that ridiculous amount of arithmetic with squares and pluses and minuses and everything, we get this width, delta omega R over L. So what does that mean? Well, back to our resonant curve. This delta omega, the width, is R over L. Okay, so if you want to find a way to get this peak to become more narrow, you could do two things. You can make the resistance smaller, or you can make your inductance bigger. So for instance, there's this really famous LRC resonator where you actually don't use regular wires made of regular metals, but you use wires made of superconducting material. And then this R goes to 0, so this peak becomes almost infinitely sharp. And for LRC resonators made of superconducting material are really quite the rave. The width is not exactly 0, but it is the closest that you will get to a 0 resonance. So let's write some important things down. The Lrc filter we have the resonant frequency 1 over Lc, and we have the width R over L, and we could combine these, and then we get a Q for quality factor. And it is, by definition, omega naught over delta omega. And therefore, it's 1 over root Lc L over R. One over R root L over C. The quality factor. There's a similar quality factor that you can define for mechanical resonators, and it's for resonators that look like this. They have some kind of a peak and very simple damping mechanism. You'll always find something like this. So what do I mean by damping mechanism? Well, this resistor is the only thing in this circuit that loses energy, because remember what I was saying before, that if there's a resistor, that microscopically what's happening in a resistance is that the electrons, when they flow through the resistor, they actually dump some heat. So the quality factor tells you how good this thing is. So the less energy that's lost, the higher the Q is. So in that sense, high Q is better. And there are all sorts of other things that you can talk about. For instance, in mechanical resonators, the losses are the hydrodynamic drag, for instance, if you're talking about a cantilever in water. So they always involve something that has some kind of an energy loss. Now, finally, let's talk about non-ideal circuit elements. Okay, the first one, the resistor. Well, let's look at resistors. Resistors are these things. They are they're usually made of they have a thin film inside, and the thin film has a very well calibrated amount of losses. And you can't read the barcode on this, but trust me, this is a resistor. But now let's look at this not as a resistor, but as a resistor with other stuff happening. So for instance, there's this, so we know inside here, it's a resistor. But this wire here and this wire here, if I were to cut out the resistor and basically cut it out and have just these two wires, then wire here and wire there would be separated by an insulating gap. So therefore, that is a capacitor. So this resistor has a capacitor in parallel. And these wires, these wires that are going to the resistor also have an inductance. So there's actually an inductance here as well. And you could put it on one side, put it on the other side. Sometimes people will put in the inductor underneath the capacitor, sometimes out. But if you look very carefully at what the geometry of this object is, it should be clear which one will work. So for instance, if you want to use this resistor in a circuit and you want to do this in an AC circuit where the frequency gets quite high, you'll see that this capacitance for high frequencies is going to start to bypass this resistor. So how do you solve that? Well, if this is the capacitance because these leads are long, you make the leads smaller. And that's why on more high frequency circuits, you'll find resistors that are really, really tiny and they have barely any lead at all. And that's also going to help you with this. So that's the resistor. Now let's talk about the capacitor. So the capacitor. This capacitor has the same leads that this one has. So there's an inductor here. What is a little harder to visualize is the resistance, because what is the losses here? Well, this thing is made of wires, and these wires, they will have some losses in them, right? So there's going to be a lossy resistor. And then also sometimes if your capacitor is filled with some dielectric material and you're running this at higher frequencies, sometimes these dielectrics, when you have a very rapidly alternating AC field, they will also give you losses, and you can write those just like a resistor, except this resistance is going to get a resistance value that is frequency dependent. And now finally this one, the inductor. The inductor has leads, so lead 1, lead 2, and I can show you why that is, because I have my inductor here. There's my inductor. I am too fast.
Yep.
Resistor. Okay, this is my inductor. You see the inductor looks just like the resistor. So if I remove this inductor from this wire, I still have one wire on the right and a wire on the left. That's a conductor and a conductor with an insulating barrier in between. That's a capacitor. So there is going to be a capacitor here. And then, of course, the wire also has losses because this thing is made of conducting material. So there's also a resistor. Sometimes you'll put this resistor inside here. Sometimes you put the capacitor across it. So if you want to be super careful, for instance, you could do it like this. So those are your non-ideal approximations to circuit elements. So when you do circuit design, any kind of higher frequency circuit design, like the stuff I do for my lab, I have to worry about these things all the time. And usually if you go to higher frequencies, all of these things start to matter. And for instance, for my DNA sequencing device, everything is high frequencies and high impedances. So it turns out to be rather tricky to do, but ultimately it's doable. If you go to really, really high frequencies, you can no longer assume that this inductance is a lumped element. but you have to really consider the finite size of it, and then you have to start worrying about stuff. So this is usually when lambda, the wavelength of whatever AC circuit is, it's still bigger than 10 times the size of the, 10 times size of the component. So it's important to see that just because you design something that has a resistance doesn't mean that there's not also, just because things are three-dimensional, capacitive coupling between things that you might not otherwise find desirable. Next chapter. Let's consider a capacitor. So I want to draw this capacitor as this wire that has a plate here and a plate there, and then we have this here. So this is our capacitor. Now we've talked about what happens with a capacitor when you charge it. So for instance, there's this current that flows, and if this current is flowing through the capacitor, somehow what we're doing is we're putting positive charges here. So we're making this thing positively charged. Let's use colors. So this thing becomes positively charged. And this one is negatively charged. And there are two ways to look at how this negative charge shows up here. So the first way to do it is we have some source of positive charges and we put them there, and because positive attracts negative, therefore the presence of these positive charges will pull negative charges from whatever circuit is attached here to the left, and it will end up on the inside of this plate on the right. So if negative charges are going to the left because they're attracted by this, that means that the current here goes to the right. And then, of course, the other way to look at it is to say, well, we've completed this circuit, we put a battery here, and we're just pulling charges from here to there to the other side. Neither of those is necessarily the only way to look at it, but they both give you the same answer, so we don't have to worry about it too much. Okay, now that's just charging a capacitor. So you might say, well, Professor Postma, why are we talking about capacitors again? Well, they're interesting. This is why they're interesting at this point. So think about the following. We have now a wire, and I drew this thing on purpose. I drew this large, and we know that current carrying wires generate magnetic fields. So we have a magnetic field, and that means that there's magnetic field lines, and I'm drawing these three-dimensionally. And of course, we have the same thing here. And we have the same thing here. And if we want to calculate the magnetic field, we can use these Amperian loops and the surface that it spans, and then we can count, okay, how much current goes through this loop, this soapy membrane. And this current that goes through it therefore generates this magnetic field, B. Okay. What happens in this region? Well, in Ampere's law that we used, the surface here doesn't necessarily need to be a flat surface. We could bulge this out. So if you remember, I like using this soap membrane as a picture. We can blow on it from this side, and then you get this bulge to go out. And you'll see that this soapy membrane, when it goes to the right, it's still going to be experiencing this current that flows through it, and it pokes a hole in the membrane, so everything is fine, up to the point where we blow through it and the membrane goes here. So let me draw that. This becomes this kind of chef's hat membrane. And now it goes through this area that has no current anymore. And the question that we need to ask ourselves, does that mean that there's no magnetic field? Well, we know that that's not true. So obviously there's something happening in this area that we need to account for, because otherwise we can't consistently say that there's a magnetic field generated here and the field we get is independent of the current that we're getting. And the thing that's going to help us is this effect that I was describing at the very beginning. When I said, if you have a current that runs through here, the reason this current flows on the other side is because there's an electric field here. And that electric field there translates the charging of this plate to the charging of that plate. So therefore, the electric field in this gap communicates the fact that there's a current flowing here and there's a current flowing there. So can we do something with the electric field in this area? That's the E field. That is confusing. Why am I using blue again? That is the E field as a function of time. So this charge is the charge that accumulates on these plates. And that charge is related to the electric field in this region through this expression, because we know that for an idealized situation, you know, plates are close together, massive plates, field is uniform. We know that this is the field. So therefore, so I had my epsilon naught on the wrong side, sorry. Let me just write this epsilon naught A E of T, just for completeness sake. Okay, so we have now some description that couples the charge on the plate with the electric field that is in the region between the two plates. And now we can say, well, if we want to convert this description of a current, instead of using the actual charge here on the plate, can we describe it as a function of what's happening in the field? And we can, because we can just take the derivative. So we take a ddt of epsilon naught A E of t. And now we get epsilon naught times A times ddt E. So now we've described the current that is charging these plates as the time derivative of the electric field that goes. And the fact that there's a time derivative is not too hard to understand, right? Because if once you hold the charge constant here, the electric field is constant, and therefore no current is flowing anymore, because if the charge is constant here, you don't need to replenish charges anymore. But as soon as we start putting more charges here, because we have a current, also the field is going to change. So it's quite reasonable to assume that that current can be described as this ddt times E. Okay, now the genius of this description is that this thing we can call displacement current. Now it's an unfortunate name because we could describe it as a current, right? Because we just did so, but it's not really a current. But this is the name that we stuck with. And if we're saying that we should be allowed to use this displacement current in addition to whatever real current there might be flowing, then we should be able to modify Ampere's law, which at this point says mu naught times I enclosed. And we should be able to add mu naught times I displacement. There we go. That's mu naught I enclosed plus mu naught epsilon naught A ddt of E. And if we integrate that, so we generalize it, then we can write this as mu naught J dA. And we can do the same thing here, mu naught epsilon naught ddt of E dA. Or put it together, mu naught integral J plus epsilon naught ddt of E dA, where this is now the J displacement. So that's the displacement current density. Okay, now this is always an argument that looks a little funny because I'm making a bunch of simplifications. So I'm assuming that these plates are nicely uniform electric fields, so big plates, and I'm assuming that I can generalize going from this A times E to a surface integral of E dA. These are not unreasonable assumptions, but of course that's not very hard. That's not a very hard rule. So if this makes you a little uncomfortable, so rest assured that there's a real reason why this thing needs to be there, and that is that there is a vector identity that needs to be satisfied. And so far, when we have Maxwell's equations, that vector identity is not satisfied. And in the margin in the textbook, you can find that version of the derivation of the displacement current. So it's not just a thing that we need for this specific physical reason, but it's also something that we need because there's a vector identity that just needs to be satisfied, and it's not unless you include this displacement current in the Maxwell equation. Okay, so now this is the new formulation of Maxwell. So this is now Maxwell 4. And we're going to call this Ampere Maxwell. We're adding Maxwell in honor of what I told you earlier, that he's the guy who figured out that there was something missing here. Okay. Now we have all of the Maxwell's equations complete. So let's put them all together. So we have 1. Gauss's law says that EDA is Q enclosed over epsilon naught. So Q enclosed over epsilon naught. Now there's another way to write this, and that is 1 over epsilon naught rho dV where this normal is pointing out of this Gaussian surface, and this Gaussian surface is the edge of this volume. So there's a volume here, and this is the edge of the volume. And the normal is pointing out. Normal is out of V. And we can define an inside and an outside because the Gaussian surface is closed. Now, Maxwell 2 says that if we take a stroll through an electric field, we originally had 0 here, but we made a change and we added a magnetic field, and that was B dA. And this is the edge of surface, this surface, and the sense of integration is related to dA vector through a right-hand rule. So right-hand rule, if we go in this direction, fingers go in this direction, that means we're picking dA this way. And that's why we can unambiguously assign a minus sign here, because otherwise we could say, like, you know, we don't really quite know which way it's going to circulate. All right, that's Maxwell 2. Now, Maxwell 3 is the one that we have messed around with the least. And that is that if we have a B dA through a Gaussian surface, then that is 0. So this BdA is not this BdA. This is BdA through an Amperian surface. This is the BdA through a Gaussian surface. So let me make sure that I do this. This is Amperian surface. And this is a Gaussian surface. And this is also a Gaussian surface. And now Maxwell 4 says that if you take an Amperian loop, then you get a mu naught times J plus epsilon naught dE dt dA, and where again this is the edge of this surface, and there's a right-hand rule that ties the sense of integration to the direction of dA, and this is again an Amperian surface. And these are the Maxwell's equations. There's a bunch of stuff that we can do. I've done this before, where I would say there's actually a where's my other color? There's a physical quantity. There's a physical quantity associated with this, and it's this phi e. So phi e, that's the flux going through that Gaussian surface. There's a physical quantity associated with this, and that's the EMF. And you can have an EMF through a non-Amperian surface, right? Because you could just have a wire that moves. But when it's a closed path, we assign the EMF to this. There's a magnetic flux here, but that's the flux through a Gaussian surface. And then there's a magnetic flux here. That's the flux through an Amperian surface. There's a line integral of B through dm. You could say that that's like a scalar potential, scalar magnetic potential, if you want to look at it that way. But then again, that's not always a useful thing. Okay, so there are so many different formulations of this, and that's why I usually start small and I start adding stuff to it. Hopefully you'll see that because these two integrals that we have on both sides, that they're tied together here, there, and there is a way where we can kind of fix this, where we don't have to worry about these integrals anymore and the sense of this tying to the sense of that. And you'll probably learn how to do that when you do Physics 311, and you'll use Gauss and Green's theorem to convert these into differential form, and it cleans them up a lot, and you don't need fluxes anymore. So this is the Maxwell's equations in vacuum. Now, in vacuum, what do we mean by in vacuum? Well, in vacuum, we mean that this epsilon naught is just whatever epsilon is. It's 8.85 10 to the minus 12 with a whole bunch of units. And this mu naught is 4 pi times 10 to the minus 7. And that's it. What if we have materials? Well, that's usually a field onto itself, where we have to modify Maxwell's equations to take care of those materials. There's one very simple change that we can make, and we will make when we start doing electromagnetic waves, and that's when we'll say, when we have waves that are traveling through transparent material like glass or water, we'll account for that by taking this epsilon naught and bumping it up a little bit. And we'll do that in a little bit. So the rest of Maxwell's equations stay the same, but all we do is change that epsilon naught. That's as far into adding materials that we will go, because materials don't necessarily need to behave that way. It's convenient that for glasses and water at particular frequencies, you can assume that all you need to do is adjust that epsilon naught, but it is not guaranteed to work for all materials, and that's also why we don't go too far. So this is Maxwell's equations in vacuum. And these are the equations in vacuum, and we can modify them a little bit, messing around with this epsilon naught and messing around with the mu for certain magnetic materials, but we're not going to do too much of that. Okay, but these are the equations that have all of the sources in. So what do I mean by that? Well, we know that this Q actually generates this E field, right? So this Q sources an E field. So this Q is the source of that E. And that Q over epsilon naught you can write as this volume integral. In this case, the time varying magnetic flux creates an EMF. So causality goes this way. Yeah, I don't know why we always write them in this order. Sometimes I think we should just adopt the shorthand to reverse them. And then the Gaussian surface, we don't need to do anything because causality doesn't run anyway if you have a 0. And in this case, this is generating the B field. So it goes from right to left in this case. Now we have several sources here. We have, let's start here. We have either some kind of a charge or a charge distribution that can generate an E field. And here we have a time varying magnetic field that can generate an E field. Here we have either a current that we can source externally or a time-varying electric field that we can use to generate a magnetic field. So the only external sources that we have, are rho and J. So if we think about Maxwell's equation as like a little box, and you want knobs on the outside to mess around with fields on the inside, these are the only things you can do. You can put charges in, and you can send currents in. If you don't do anything, so you don't have any sources, then usually you can set these things to 0, and then the equations become even a little bit more simple. So if you don't have a source here, this EDA is 0. That's nice because this VDA is 0. You have just this. EDL is the minus DDT of VDA. That's not modified. And then this one is VDL is mu naught epsilon naught DE dt. I hope that you see that that actually increases the symmetry in these equations, because then all of a sudden this equation has a 0 for both the E Gaussian integral and the B Gaussian integral. So Maxwell 1 and 3 in their sourceless form have a 0 and a 0. Maxwell 2 and 4 also look very similar because there's an EDL and then there's a DDT on the right. And then there's a BDL and a DDT on the right. So let me write that down, but now I'm going to write them in causally correct manner. So Maxwell 1, sourceless. Sourceless Maxwell's equations. So Maxwell 1, that one we don't have to worry about because that's 0. Maxwell 2, we have the DDT of BDA creates minus EDL Maxwell 3 is now looking just like Maxwell 1, and Maxwell 4 is saying that there's a mu naught epsilon naught DDT of EDA creates a magnetic field. And I hope you see how nicely symmetric this is, right? So these are to 0. These two give you time dependence of B that generates an E, and a time dependence of E that generates a B. And these two things together are going to generate electromagnetic waves. So we'll get time varying magnetic field creates an electric field. That in turn, time varying electric field is going to generate a magnetic field again. And these two things together are going to set up a wave equation where one causes the other and in a cyclic process, and that's how you get waves. So these are the sourceless Maxwell's equations, and this will be the starting point for the wave equation, electromagnetic waves, and then afterwards for optics.